Okay, so we're going to jump in and I'm going to walk through the process of working through the problems on our reaction rate and rate law homework. So we're going to start with 5.1, which is all about reaction rates and things that affect reaction rates, and using stoichiometry to determine rates with respect to different reactants and products. So we're going to start with this we do that says the rate of disappearance of ozone is negative 0.0034 molar per second. Remember that molar per second is moles per liter per second, because it tells us that this is the rate of disappearance of ozone, and that's why it's a negative number, because it's disappearing. So we're going to go ahead and take that number that is the disappearance of ozone, and that's moles of ozone. And we're going to apply the balanced molar coefficients to that. So we know that for every 2 moles of ozone, there are 3 moles of oxygen. And so we get, but that's for every 2 moles of ozone that disappear, 3 moles of oxygen up here, so we're able to get rid of that negative sign. And so we can say that this is 0.0051 moles of oxygen per liter per second. Or we could write this as 0.0051 molar per second of oxygen. Either one is okay. Now when it asks for the rate of reaction, this is per mole of reaction, and so we want to reduce this down to a 1 in front of the ozone. So we're going to, again, go with the negative 0.00 moles of ozone per liter per second times 2 moles of ozone for every 1 reaction, and that's going to give us 0.0017 moles of reaction per liter per second. Okay, so this is our first experience with the idea of per mole of reaction. We'll see this a lot more often in thermodynamics. Okay, so now we're moving on to the problems where you guys begin. So we're collecting data. We can see that this is a 1 to 2. So for every 1 mole of dinitrogen tetroxide that disappears, 2 moles of nitrogen dioxide are going to appear. Since 0.0500 moles disappeared, we know that 0.1000 moles are going to appear. And we're going to follow that same pattern. Whatever this changes by, we're simply going to double it over here. But since this concentration is increasing, we're going to double the change and add it to the previous number. So this changed by 0.0250. We're going to double that to get 0.0500, and we're going to add it to the 0.100, so we have 0.1500. Again, this changes essentially by an eighth, so we're going to go with 0.1750, and this is going to be 0.1875. So we've completed our table here, and now we're going to graph our data. So we know that this starts at 0.2000, and after 100 seconds, it's down to 0.15. And after 200 seconds, it's down to 0.1250, which is right here. And after 300 seconds, it's down to 0.1125. And after 400 seconds, it's down to 0.1063. And so we're just going to draw the curve that best fits this. So we're looking for a line of best fit, and because this concentration is decreasing and the rate is decreasing, we're not expecting this to be a straight line, we're expecting it to be a curve. I don't have blue here, so we're just going to pretend that that's a blue line. We're then going to do the same thing with the concentration of the nitrogen dioxide. It's going to start at 0. It's going to jump up to 0.1, then jump again to 0.15, then up to 0.175, and then up to 0.1875. And again, just a curve that's a line of best fit. Whoops, that was more of a line than a curve. And this is why I teach chemistry rather than art. And there's our line of best fit. And you'll notice that this one is changing twice as rapidly as this one. All right, so if our being produced at a rate of 0.397 molar per second, and that's ammonia, again, just a stoichiometry problem. We're going to say that for every 2 moles of ammonia, there's 1 mole of nitrogen, and that would give us whatever half of 0.397 is. 0.198 molar per second of ammonia, of nitrogen, and then we're going to do the same thing, 0.397 molar per second of ammonia, and for every 2 moles of ammonia, there are 3 moles of hydrogen. So that's going to give us 0.596 molar per second in terms of hydrogen. So just a simple stoichiometric equivalence. Oops. Okay, now you can see the work. Sorry, 0.397 times 1 divided by 2 gives us the 0.198, and 0.397 divided by 2 times 3 gives us 0.596. All right, so now it's asking us to do something with this overall ionic reaction for the decomposition of bleach with a cobalt-2 nitrate catalyst. And you see that the cobalt is being listed as a catalyst here. That's why it's above the arrow. So first, a review question that asks us to write the net ionic equation for this reaction. So we're going to take a look at our reaction. And we're going to notice that we have sodium ions on the product side and on the reactant side. So we're going to cross those out. And the only things that we're left with are the hypochlorite ion, the chloride ion, and oxygen. So we're going to write those as our net ionic equation. So we had the hypochlorite ion, the chloride ion, and oxygen. So just a quick review of net ionic equations. Okay. It tells us that we use 6% extra strength bleach at room temperature. 100 milliliters of oxygen gas was produced in 2.03 seconds. And it asks us to calculate the... So, generally speaking, rates are calculated in... they're sometimes calculated in terms of partial pressures. They are often calculated in terms of molarity, and they are sometimes calculated in terms of moles, but they are rarely calculated in terms of volume. So the first thing that we're going to do is convert this volume of oxygen gas to a number of moles of oxygen gas. So we're going to use PV equals nRT because it tells us that it's at room temperature. So we know that we can't use 22.4 liters because it's not standard conditions. So our temperature at room temperature is probably 23 degrees Celsius. We could use 25, that's kind of the standard. So let's go ahead and use 25. plus 273 to give us 298 Kelvin. And the pressure we're going to assume is 1 atmosphere. And so when we plug everything in, we get that 1 atmosphere times 0.1000 liters equals some number of moles times R, which is 0.08206 liter atmospheres per mole Kelvin, times our temperature in Kelvin, which is 298 Kelvin. So we have 0.1 divided by 0.08206 and 298. And that's going to give us a number of moles of 4.09 times 10 to the negative third moles. So we have a change of 4.09 times 10 to the negative third moles in 2.03 seconds. That's our rate, because that's our change in moles divided by seconds. And that gives us 2.01 times 10 to the negative third moles per second. So that's our answer to B. Now C says that this reaction produced gas too fast to record useful data. So it asks 2 ways to slow the reaction down. Well, it tells us that it was catalyzed by the presence of the cobalt-2 nitrate. So the easiest thing to do is to remove the catalyst, because that's going to slow down the reaction by increasing the activation energy. We could also perform the reaction at a colder temperature, so we could decrease, I can't spell, the temperature. That would slow down our reaction, because it would mean that fewer of our collisions would have sufficient activation energy. We could decrease the concentration of bleach. So all of those would be options for decreasing the speed. Okay, so this question asks us if these 3 students all react zinc with hydrogen ions to form hydrogen gas and zinc ions, which students' conditions would produce the hydrogen gas the slowest? Well, we have powdered zinc and zinc strips. The powdered zinc has a higher surface area, so it's going to react faster, so that's not going to be a good choice. This one has twice the concentration of hydrogen ions that the hydrochloric acid does, so that's going to make it faster, so that's not a choice. And then of these, the lowest temperature, so student 2, because of low surface area, low concentration, and low temperature, is going to be the slowest. And then it says which substance was oxidized and which was reduced. Remember that oxidized means that it loses electrons, and reduced means that it gains electrons. So since this goes from a 0 to a +2, that means that the zinc lost electrons. So the zinc is oxidized, and the hydrogen ions go from a +1 to a 0, so they have gained electrons. So the hydrogen ions are reduced. Okay, let's slide this down. Our gaseous xenon tetrafluoride can be synthesized from xenon and fluorine. So write the balanced chemical equation. Again, this is simply review. So we have xenon plus 2 fluoride yields xenon tetrafluoride. It says if the initial rate of appearance is xenon tetrafluoride is 2.5 times 10 to the negative 2 atmospheres per minute. So here we have an example of measuring rate of appearance in pressure. What is the rate of disappearance of xenon? Well, since these are 1 to 1, it's going to be the same. If they were not 1 to 1, we would need to do some calculations, but since for every 1 mole of xenon tetrafluoride that's formed, we consume 1 mole of xenon, we can say that it is negative 2.50 times 10 to the negative second atmospheres per minute. It would be okay as well to leave this as a positive number since we are talking about a rate of disappearance. And then it asks us to draw the Lewis structure for xenon tetrafluoride. So we know that xenon has 8 electrons, fluorine has 7 times 4. So we have a total of 36 valence electrons. So we have our xenon. We're going to put the 4 fluorides around it. Fluorines around it. Okay. So we have, once we get all of these valence electrons around here, we will have gotten to 32 valence electrons. So there's 34 and there's 36. So we can see that we have 6 areas of electron density and we have 2 lone pairs. So maybe 90-degree angles. Okay.